All right, welcome to the deep dive. Today, we're taking a look at something pretty wild. It's about how machine learning is totally shaking up the way we optimize FPGAs, those field programmable gate arrays.
Definitely shaking things up.
Yeah, so for anyone who maybe hasn't worked with these things before, FPGAs, they're like the heavy lifters in a lot of modern tech. Super versatile, high performance, you name it. But here's the thing. They've got this finite set of resources, right? You've got logic elements for the actual computations, memory blocks to store data, and then DSP slices, which are kind of specialized for signal processing. And the big puzzle for designers is figuring out how to get the most out of these resources because they're limited.
It's absolutely crucial to manage these resources efficiently, and it goes way beyond just making the circuit work, right? You need to hit that performance target, keep power consumption in check, which is becoming a bigger and bigger deal these days, and of course, meet those project deadlines, which, let's be honest, are often pretty aggressive.
Yeah, for sure. So if you don't do a good job with optimization, you could end up with bottlenecks that, bottleneck everything. You might see your power bills skyrocket, and then those dreaded project delays start creeping in. Nobody wants that.
Nobody wants that. Oh.
So what we're going to do today is dive deep. That's why it's called the deep dive into how machine learning is emerging as this almost a shortcut to better FPGA resource optimization. We've been poring over all this research, and there are some pretty surprising insights into how ML is going way beyond those traditional manual methods. And frankly, those older methods, well, they had their limitations. I mean, you're dealing with the fixed nature of these resources, those logic units, the memory, DSPs, and it's this constant struggle to balance speed requirements, try to be energy efficient, and then navigate the incredible complexity of how all the pieces get connected on the chip. And to top it all off, you're wrestling with these EDA tools, electronic design automation tools, to get them to do what you want. It often felt like a ton of manual effort and required some serious specialized expertise.
Yeah, and what's really revolutionary here is that machine learning is changing the entire game for EDA, for FPGAs. Yeah. So instead of just sticking to those predefined rules and those kind of classic analytical models, we're now seeing this incredible ability to learn these super complex relationships directly from data. Yeah. And we're talking mountains of data. This data-driven approach, it's becoming a part of every single stage of FPGA design. It starts at the high-level synthesis, where you're basically describing what you want the hardware to do, and it goes all the way down to the nitty-gritty steps of physically placing those components and routing all the connections between them.
I think it helps to really visualize this. There's this cool figure 1 from one of the research papers we looked at that really maps out this whole landscape of how ML is being used in FPGA EDA. It's quite impressive, the breadth of applications.
It really is.
For example, we're seeing it used for quality of results or QOR estimation. That's like predicting how good your design is going to be in the end. Stuff like estimating power consumption using these things called regression models. Right. Then there's hyperparameter selection, where reinforcement learning is actually helping figure out the best settings for those synthesis tools that are taking your design and turning it into hardware.
Yep.
And design space exploration. Algorithms like genetic algorithms are being used to find those really sweet spot designs that balance all these competing goals like performance and how much of those resources you're using.
That's a big one.
And when you get down to the actual physical implementation on the chip, we see things like convolutional neural networks being used for placement. They can predict areas where you're going to have a lot of congestion.
Makes sense.
And then graph neural networks are tackling routing, which again is all about figuring out where you might run into bottlenecks when you're trying to connect everything up. So it's really interesting to see this broad range of applications, all driven by ML.
And I think if you step back and look at the bigger picture, the potential here for ML to really break through the limitations of those traditional EDA tools is huge. Especially when we're talking about trying to predict how our designs are going to behave as semiconductor technology keeps marching forward, with smaller transistors and more complex chips.
Yeah, absolutely.
What's really key here is that because machine learning is all about learning from data, it can adapt to these really challenging scaling issues way better than those old analytical models, which often rely on, simpler assumptions about how the hardware actually works.
Okay, so let's zoom in on one of these applications, something that I think is really valuable to designers, predicting FPGA resource utilization. What we're talking about here is getting an estimate of how many of those precious resources, the logic units, the memory blocks, the DSPs, your design is going to gobble up before you go through this whole long process of actually implementing it on the FPGA.
Right.
You can probably already see how valuable that would be, right?
Absolutely.
If you can predict that early on, designers can make smart decisions about their overall approach right from the get-go, and you can avoid those nightmare situations where you suddenly realize, oh no, I'm out of this one crucial resource.
Absolutely. And what's been really powerful in this area is the use of these things called regression models. Basically, these are machine learning algorithms that learn from tons and tons of historical data. And this data is all about past designs and how many of each resource they actually used after they were implemented.
So they're learning from experience, kind of.
Exactly, learning from experience. And once these models are trained, they can then look at a new design one they've never seen before and make a really good estimate of how much of each resource it's going to need. So how much RAM, how many DSPs, FFs, and LETs. Some of these models can even predict how many clock cycles it'll take for a machine learning model itself to run on the FPGA. That's pretty amazing, right?
Yeah, that is pretty wild. So they're finding these hidden relationships between how the design looks and how it actually uses the FPGA's resources. Now, I think a lot of people, when they hear machine learning, they think super complex algorithms, deep neural networks, that kind of thing. But it's interesting that sometimes these simpler regression models, the kind that just fit a straight line or a curve to the data, can be surprisingly good, especially when you're predicting a specific resource or working within a certain design style.
Yeah, for sure.
Like we saw examples of how they've been used to estimate the number of flip-flops, those basic memory elements in multi-layer perceptrons, which are a kind of neural network just based on the number of neurons and how they're connected.
Right.
So these simpler models, they can really quickly capture those more direct relationships.
Exactly. And what's also really cool is that we're starting to see specialized open source tools popping up, like this tool called Rule Form Editor. What Rule Form Editor does is it uses pre-trained regression models to give you instant predictions.
Yeah.
I mean, it's almost instantaneous about how many resources your design is going to use and even how long it'll take for your ML model to run on the FPGA. And here's the kicker. It does all of this before you've even gone through the whole synthesis process, which, as you know, can take a lot of time.
Yeah, it can.
So these tools, they're really bridging this gap between designing your machine learning model and actually getting it to run on an FPGA. And they're giving engineers this early look into whether their design is even going to be feasible in terms of resources.
It's like a sneak peek, right, before you commit to the whole process.
Exactly.
So I'm curious, what are these models actually looking at to make these predictions? What are the key things about a design that they're analyzing?
That's a great question. So there are several features, you could say, that are derived from the design itself and the high-level synthesis process, or HLS, that are really important.
Okay.
So HLS, just a reminder, it's the process of taking a high-level description of what you want your hardware to do. Usually you write this in a language like C++, and turning it into the actual hardware implementation.
Okay, got it.
So some of the features that these ML models pay attention to, they include things like the data precision. That's like how many bits you're using to represent the inputs, outputs, weights, and biases in your design. Then there's the reuse factor of the FPGA's multipliers, which tells you how efficiently those specialized DSP resources are being used. Then you have the optimization strategy that you've chosen, like are you telling the tools to try and minimize resource usage? Or are you going for maximum performance and the lowest latency possible? And then, of course, the specific FPGA board you're targeting matters a lot because different boards have different amounts of resources, and those resources might be organized a little differently on the chip.
Right. So those HLS parameters, they're really influential because they're basically determining how much parallelism you're going to have in the hardware and how complex that hardware is going to be.
Exactly. And when you're talking about these really specialized MLPs, those multi-layer perceptrons that are designed for TinyML, which is all about these really small-scale machine learning deployments, often on devices with very limited resources. Resource estimation often comes down to the very specific topology of the model, the architecture of any hardware accelerator you might be using to speed things up, and even the specific values of the network's weights.
Oh, wow.
Yeah, so the way a machine learning model is put together and implemented at this low level can really impact how much of those FPGA resources it needs. For example, if you're making very deliberate design choices, like forcing the model to share weights between different parts of the network, it can change the resource usage in ways that are pretty different from, those more general purpose implementations.
So it's not just about the model itself, it's about how you're implementing it on the hardware too.
Precisely.
And it sounds like even the information that you get earlier in the process from that high-level synthesis intermediate representation, which is like this more abstract view of your design before it's completely turned into hardware that can also be useful for prediction, right?
Oh, absolutely. By analyzing the design at that higher level, before all those low-level details are finalized, the ML model can get a good sense of how data is going to flow through the design and the sequence of operations that are going to happen.
Okay.
And this has been super helpful for predicting things like routing congestion. That's where you might have too many connections trying to squeeze through the same pathways on the FPGA.
Makes sense.
So it gives you this earlier and often more accurate picture of the overall resource needs by looking at the big picture, the overall data flow.
So to sum up, what are the main advantages we get by using ML for this pre-implementation resource estimation?
Well, there are a bunch of benefits, actually. First off, as we've talked about, you get these really valuable early insights into whether your design is even going to fit on your FPGA and how efficiently it's likely to run. This naturally leads to a much faster development and deployment process because you can quickly try out different design ideas and see how they'll perform.
Right.
And by finding those potential resource bottlenecks early, you avoid those really painful and time-consuming redesigns later on. It's also a great way to empower both the design engineers and the machine learning experts to quickly evaluate their ideas without having to wait forever for those HLS runs to finish. It just makes the whole process so much more agile. You can try things out, prototype quickly, and explore a wider range of possibilities.
You get to be more creative, maybe.
Exactly. And then there's the speed. I mean, we're talking about resource predictions that happen in milliseconds compared to the minutes or even hours it can take with traditional HLS. That's a game changer, especially in the early stages of design.
Yeah, that makes a huge difference. All right, so let's move on to another really critical part of FPGA design, placement and routing. Now, as we mentioned earlier, how those logic blocks are arranged on the FPGA is super important for how well your design is going to perform and how efficiently it's going to use those resources.
Right.
And it sounds like machine learning is making a big impact here too, especially in predicting and helping to avoid routing congestion during the placement phase.
Definitely. We're seeing some really interesting ML models being developed specifically to estimate where routing congestion, those bottlenecks in the connections between components, is likely to occur. There's one model called ML-Kong, and it's been showing some pretty impressive results. It can predict congestion with about 85% accuracy, which is pretty good.
That's pretty good. Yeah.
And what's really cool is that it's much faster than traditional global routing algorithms. So you can get this quick assessment of potential congestion issues very early on in the placement process, which gives designers time to adjust their strategy.
So it's like a heads up, basically. Right. And then there's another model, DL-Kong, that tries to improve on this even further, right?
Yep. DL-Kong uses a deep learning approach. Mm-hmm. It's based on this thing called a convolutional encoder-decoder. And this more sophisticated approach allows it to get even higher accuracy in congestion estimation, up to 94% in some cases.
Wow.
And it can still run really fast, like under a second. The cool thing about this convolutional method is that it's better at understanding the spatial relationships between how the logic blocks are arranged on the chip so it can pinpoint those congestion hotspots more accurately.
That's impressive. It's not just about predicting congestion, though, is it? I remember reading about work where they're actually trying to predict whether a particular placement of components can even be routed at all.
Yeah, that's right. Researchers are using these CNN-based frameworks, those convolutional neural networks, again, to predict whether you can actually route all the connections for a given placement.
Right.
And they're doing it with really high accuracy, like around 97% in some cases, and in just milliseconds. And that's super valuable because it lets the placement tools avoid wasting time on configurations that are probably going to fail in the routing phase, where you're actually connecting everything up. It increases the chances of finding a good overall design solution.
It's like avoiding those dead ends before you even get there.
Precisely.
And since FPGAs are basically massive networks of interconnected components, it makes sense that those graph neural networks, or GNNs, are being applied to placement optimization too.
Absolutely. GNNs are perfect for dealing with these graph-like structures that we see in circuit net lists, which are basically descriptions of how all the components in your design need to be connected. These GNNs can learn these really cool embeddings, which capture the relationships and dependencies between different components.
Okay.
And this learned understanding, this knowledge, can then be used to guide the placement process, helping to find better arrangements of components, ones that minimize wire lengths and make routing a lot easier.
It's like teaching the algorithms to think about the problem more like a human would.
In a way, yeah.
I was really intrigued by the idea of combining reinforcement learning with more traditional placement algorithms, like simulated annealing, which has been used for ages.
Yeah, that's where you see approaches like RL Place coming in. What they do is enhance that classic simulated annealing method by adding a reinforcement learning agent to the mix.
Okay.
So this agent learns from its experiences during the placement process, and it can choose from a set of moves that are specifically designed to improve those key metrics like wire length and timing performance. So it's not just making random changes, it's making more informed decisions based on what it's learned. And this leads to a much more intelligent exploration of all the possible placements compared to, just randomly tweaking things like in standard simulated annealing.
So it's learning how to place the components in a way that's going to make routing easier and improve performance.
Exactly.
So once all those logic blocks are placed, the next step is to route all the connections between them. And it sounds like machine learning is finding a role in optimizing this stage of the design process as well.
Oh, absolutely. Just like with placement, we're using ML to predict routing congestion. By finding those areas where you're likely to have a lot of connections trying to squeeze through early in the routing process, designers can potentially go back and tweak the placement or even go back to the HLS stage to make the design easier to route. Predicting those routing bottlenecks early on can save a ton of time and headaches down the line.
And that reinforcement learning approach we talked about, that pops up in routing optimization too, right?
It does. Reinforcement learning can actually be used to turn the whole process of finding those routes into a training exercise for an RL agent. This agent learns how to route things efficiently by basically trying things out and seeing what works.
Oh, interesting.
So it gets rewards based on how well it minimizes congestion, those traffic jams of connections, and the overall length of the wires. This often involves these greedy strategies where the agent tries to make the best local decision at each step, but it's also guided by these carefully designed reward functions that encourage it to find good solutions quickly.
So it's learning how to route efficiently by being rewarded for making good choices.
Exactly.
And we talked about graph neural networks for placement. Are those also being used to optimize routing?
Yeah, they are. GNNs are being used in routing optimization as well. By analyzing the connectivity patterns in the circuit net list, they can predict potential congestion and even estimate this thing called pre-routing slack.
Okay.
Pre-routing slack is basically a measure of how much timing margin you have before you actually do the routing.
Right.
And having this information is really helpful for those routing algorithms. It allows them to prioritize the connections that are really critical and avoid creating timing violations where signals arrive too late.
So it's like giving the routing algorithms a roadmap to follow.
Exactly.
So if we focus specifically on how reinforcement learning is being used in both placement and routing, what are the key takeaways there?
Well, with RL Place, which enhances simulated annealing, you see how letting an RL agent make smarter decisions about where to place components based on the goal of having shorter wire lengths after routing can lead to placements that are not only more compact but also inherently easier to route, which often translates to better performance. We're also seeing these cool hybrid approaches where they combine RL with other machine learning techniques like support vector machines or SVMs. So you might have an SVM that's trained to predict whether a given placement is likely to be routable, and then the RL agent uses that prediction to guide its decisions as it tries to improve the placement and routing.
So it's like combining the strengths of different ML methods.
Exactly, getting the best of both worlds.
So we've talked a lot about resources and how to fit everything onto the FPGA, but power efficiency has become such a crucial factor in modern electronics, especially with FPGAs showing up in more and more portable and embedded devices.
Oh, absolutely. Power efficiency is everything these days.
And it's great to see that machine learning is being used to tackle this challenge as well.
For sure. ML is providing some really exciting new techniques for predicting and optimizing power consumption in FPGA designs. For example, we have ML algorithms that can predict both the execution time of an application on an FPGA and how much power it's going to use.
Okay.
And having this information up front allows designers to make smarter choices about the architecture of their system and how they implement it, pushing them towards options that are just naturally more energy efficient.
So they can make those decisions early on before they get too far into the design process.
Right. And I remember coming across this term, ensemble machine learning methods, which seem to be particularly effective for predicting power consumption. What's the idea behind those?
Yeah, so ensemble methods basically work by combining the predictions from multiple individual machine learning models. The idea is that by taking advantage of the different strengths and perspectives of several models, you can often get a more accurate prediction than you would with just one model on its own.
Oh, that's clever.
So for power prediction, these ensemble methods might look at information from different parts of the design process. They might look at the LLVM intermediate representation, which is what the compiler produces, the original source code itself, and even how the application behaves when it's actually running. And by looking at the problem from these different angles, the combined model can often give you a much more reliable power consumption estimate.
So it's like getting a second or third or even fourth opinion, but from different experts.
Exactly. And it looks like machine learning can also play a role in managing power dynamically within the FPGA while it's actually operating.
Yeah, absolutely.
Yeah.
People are working on these AI-driven algorithms that can adjust how much power different parts of the FPGA get in real time based on what's happening, the workload.
Okay.
So, for example, if one part of the FPGA is super busy crunching numbers, while another part is just chilling, the power management system can dynamically give more power to the busy area and less to the idle one.
That makes a lot of sense.
Right. So it's about optimizing energy use on the fly, using less power when resources aren't needed, and making sure there's enough power available when performance is critical.
So it's all about efficiency, really.
Totally.
Now, what about dynamic voltage and frequency scaling, or DVFS? That's a well-known technique for saving power in processors. How does ML fit into that for FPGAs?
Well, ML can make DVFS even more effective by predicting what the workload is going to be in the future.
Okay.
So by predicting when the FPGA is going to be heavily used and when it's probably going to be relatively idle, ML models can tell the DVFS controller to proactively reduce clock speeds or even lower the operating voltage during those expected low-activity periods.
So it's like planning ahead.
Exactly. Planning ahead to save energy without sacrificing performance when it's actually needed. And we're also seeing ML models that analyze past usage patterns to predict these demands, allowing the system to preemptively lower those clock speeds during times that are statistically likely to have low utilization. And taking it even further, some researchers are exploring embedding AI models directly onto the FPGA itself.
Wow, like having a tiny AI brain right on the chip.
Exactly. And these on-chip models could analyze the current workload in real time and make really fine-grained adjustments to power levels and resource allocation all on the fly.
It's pretty mind-blowing how much potential there is here.
Yeah, it really is.
So we've talked about all these cool concepts, but I always think it's more interesting to see how they play out in real-world situations. Do you have any examples of machine learning being used successfully for FPGA resource optimization?
Oh yeah, there are some great examples. For predicting resource utilization, the tool Rule 4 Milli is a really good example. It's been incredibly accurate in predicting those key FPGA resource usages, BRAM, DSP, FFs, and LUTs, as well as the latency of neural networks. And it could do all this before the design is even implemented.
That's impressive.
Yeah, it's really cool. And the fact that its predictions match up so well with the actual results after implementation, it shows you the power of ML for early-stage design assessment. Another great example is this resource estimator that's part of the HL4 Millilito workflow.
Okay.
Now, HLS4 Millilito is used to deploy ML models on FPGAs, and this estimator can accurately predict the resource usage for these custom MLPs, specifically how many LUTs, FFs, and DSPs they'll need, and it can do it in less than 147 milliseconds.
Well, it's fast.
Right, and that's much faster than traditional HLS tools. It shows you how ML can learn the resource characteristics of these very specialized hardware architectures.
Very cool. What about some examples of ML in action for optimizing placement and routing?
Yeah, so MLCong, with its 85% accuracy in predicting routing congestion, and the fact that it's so much faster than conventional global routers, it's a great example of how ML can give you that early feedback on routability. And then you have DLCong, which takes it up a notch to 94% accuracy using a deep learning approach. It shows how these more advanced models can capture those more complex spatial relationships between components. And then RLPlace, using reinforcement learning with simulated annealing, has shown real improvements in the quality of the placement solutions and the time it takes to find them compared to traditional placement tools.
So those are some really tangible results.
Yeah, definitely.
And lastly, any real-world applications where ML is helping to improve power efficiency?
Oh, for sure. There's this really cool example of a smart surveillance security camera that uses an FPGA to accelerate facial recognition. And they're using quantized convolutional neural networks, which is a technique for making the models more efficient. And this implementation on the FPGA achieved a 50% reduction in power consumption and a 4-fold decrease in latency compared to running it on GPU.
Wow.
So that's a huge win for efficiency. And then in the medical field, there's a portable ultrasound device that uses an Intel FPGA for AI-driven anomaly detection. They were able to get real-time results in remote areas, which is amazing, and it was 3 times more efficient than running the same algorithms on a TPU.
That's fantastic.
Yeah, it's really making a difference. And broader research suggests that FPGAs can be almost 10 times more power efficient than GPUs for certain deep learning tasks.
That's significant.
Yeah, and the big reason for that is that you can create these very customized hardware implementations on FPGAs tailored to the specific needs of the algorithm as opposed to the more general purpose and often more power-hungry resources that you have on a GPU.
So it's all about specialization, really. Okay, so we've seen all these benefits of using ML for FPGA resource optimization. Can we recap some of the most compelling advantages for our listeners?
For sure. So one of the biggest benefits is that ML is giving us more accurate predictions. We're talking about better predictions for resource utilization, routing congestion, and power consumption.
Okay.
And ML can often make more precise predictions compared to those older analytical methods because it's learning from data, from real-world examples.
Right.
And this, in turn, lets designers explore all those different design possibilities much faster. They get early feedback on how different choices are going to impact things like performance, resource usage, and power consumption.
So it's about making smarter decisions earlier in the process.
Exactly.
Yeah.
And all of this leads to a better overall result. You get better timing performance, shorter wires within the FPGA, less routing congestion, and all because ML is helping to guide those placement and routing decisions.
That makes a lot of sense.
And we're also seeing big improvements in power efficiency. ML can predict power consumption more accurately, and we have these ML-driven power management systems that can adapt to changing workloads dynamically.
That's really impressive.
Yeah. And on top of all that, ML can automate a lot of the more tedious and time-consuming tasks that are part of the FPGA design process, like fine-tuning the parameters of those CAD tools, or even picking the best design flow for a particular project. So it's freeing up engineers to focus on the more creative, higher-level aspects of design.
And probably reducing errors, too.
Absolutely. Reducing errors and speeding up the whole process.
But as with any new technology, there must be some challenges and limitations, too, right? What are some of the things that people should be aware of when it comes to using ML for FPGA resource optimization?
Yeah, you're absolutely right. There are definitely challenges. One big one is that you need a lot of data to train these ML models. I mean, a lot of data. And it needs to be good quality data, too. Yeah. These models learn from examples, so you need these large data sets of past designs and information about how those designs were implemented. And gathering this kind of data and making sure it's good quality, that's a big job.
So data is key.
Data is key, absolutely.
Yeah.
And then there's the issue of bias. If the data you use to train the model isn't diverse enough or it has biases in it, the model might not perform well on new designs that it hasn't seen before.
Right. It needs to be able to generalize.
Exactly. And then there's the black box problem. Some ML models, especially those deep learning models, can be really complex, and it's not always clear why they make a particular prediction or decision.
Yeah, that lack of transparency can be a bit unsettling.
It can. And it can make it harder to trust the model's results, especially when you can't fully understand the reasoning behind them.
And how about integrating these models into existing EDA tools? That must be a challenge, too.
Yeah, integration is a big challenge. Those commercial EDA tools, a lot of them are proprietary, closed source. So getting these ML models to play nicely with them can be tricky. And another limitation is that an ML model that's been trained on a specific type of FPGA or a particular design style, it might not perform that well on something totally different.
Right, so you might need to retrain it.
Exactly, might need to retrain it or adapt it. And then there's the computational cost of training these models, which can be really high. You need a lot of computing power and some specialized expertise to get it done. And lastly, there just aren't that many open source benchmark data sets specifically designed for evaluating ML in FPGA design, which makes it harder to compare different approaches objectively.
So those are some real hurdles that need to be overcome.
Definitely. But researchers are making progress all the time.
Well, this has been a really fascinating deep dive into the world of machine learning and FPGA resource optimization. It's clear that ML has the potential to revolutionize how we design these systems, making the process more efficient, more effective, and much faster.
Absolutely.
And those real-world examples we talked about, They really show how this is already happening.
It's exciting to see the impact it's having.
So, to wrap things up, here's something to think about. With all the amazing progress we're seeing in both machine learning and FPGA technology, what new possibilities are just around the corner?
It's an exciting time, that's for sure.
Could we eventually see, fully AI-driven design flows where the algorithms do all the heavy lifting? And if that happens, how would it change the way we design electronic systems?
That's a big question.
It is a big question. So think about how these advancements might affect your own work or the field you're in. It's something to keep an eye on. Thanks for joining us on The Deep Dive.